So I want you to imagine that you're in your car on the highway and you're sitting at mile marker 0 and you start driving forward. If you were to drive forward at 60 miles an hour for 2 hours, then you'd be at mile marker 120, right? Well, then you slow down and you drive 20 miles an hour for 3 hours. Then you're sitting at mile marker 180. So you've driven, on average, 36 miles an hour. You covered 180 miles in 5 hours. And notice how it doesn't really matter that you drove fast and then you drove slow. The only thing that matters is you were at 0, now you're at 180, and it took 5 hours to do it. So average rate of change is this computation. It's delta y over delta t. You need an interval. You need a beginning time and an end time. And using those two times, you need a beginning position and an end position, and then you can compute average rate of change or average velocity. Here's a different kind of problem. If you were to drive forward 60 miles an hour for 2 hours, and then you drive backwards 40 miles an hour for 3 hours, you cover a net distance of 0 miles in 5 hours. And that means that your average rate of change is 0. And if that feels strange, here's an illustration. So you know that you start at the beginning. We're driving forward for a while, we're driving forward for a while, and in 2 hours we've gone all the way to mile marker 120. And then we start driving backwards. So after 1 hour, we're back to 80. After 2 hours, we're back to 40. And finally at the end, you're back to where you started. So sure, the car covered 240 miles, but the net change of position is 0. We are back to where we started. Average rate of change is 0 miles an hour. Here's another example that we're going to do graphically, and I want to compare average rate of change to the slope of the secant line. So let's suppose I have this function modeling the position of a car. It's a different kind of function, and I want to know what the average rate of change is from 0 to 5. So what I need is beginning position, end position, beginning time, and end time. And so this is the computation that I'm going to do. F of 5 and f of 0 I can read from the graph. I get 60, I get 0 over 5 minus 0, and so my average rate of change is 12. On the graph, what you do is you plot the line between the 2 points. Nobody cares what's going on here. All you got to do is take your end point and your beginning point and draw that straight line. And I want you to notice, by doing old school rise over run, that the slope of this line is 12. If you go over 1, you go up 12. Over 1, up 12. And so the slope of the secant line is exactly equal to the average velocity. So here's a different kind of example of a function that you might work with, say, in calculus. We want to estimate the average rate of change from t equals 2 to t equals 3. So all you got to do is you plot a point at 2, f of 2. You plot your other point at 3, f of 3. And then you connect those two with a straight line. That is the secant line between t equals 2 and t equals 3. And what's the slope of that? Well, we can compute that off to the side. This is going to be how we compute that. By reading off of the graph, I would say that f of 3 is about 3.4 and f of 2 is about 2.9. And so that average rate of change is about 0.5. There's a second question here. Is this higher or lower than the instantaneous rate of change at t equals 2? Well, you may know that that is equal to the slope of the tangent line. So I've kind of ballparked what the tangent line is here in gold. And so that tangent line is the same as instantaneous rate of change, the slope of the tangent line. And so here, this green line, right, this is the average rate of change from t equals 2 to t equals 3. And can you tell how the gold line has a higher slope? It's steeper. Well, that means that the green line has a lower slope than the yellow.